Hello, and welcome to another extraordinary journey, this time toward Europa. I'm Dr. Eli Hart, and I'm glad to have you with me. Imagine a world where sunlight never reaches the surface, yet an ocean, twice the size of all Earth's oceans combined, moves silently in eternal darkness beneath miles of ice. This is Europa, one of Jupiter's most enigmatic moons. Beneath its fractured, frozen shell lies a vast, global saltwater ocean, kept warm not by the sun, but by the immense gravitational forces of a giant planet. Here, chemistry, energy, and water, three essential ingredients for life, may be working together, hidden from view. Today, we journey to Europa, a frozen moon that may be one of the most promising places in our search for life beyond Earth. Europa is one of those worlds that, according to early planetary science, should never have been considered alive. It is small, frozen, distant from the sun, and relentlessly bombarded by radiation. For decades after its discovery by Galileo Galilei in 1610, Europa was little more than a point of light, an icy companion orbiting Jupiter, itself considered hostile and violent. Yet today, Europa stands at the center of modern astrobiology. To understand why, we must first confront how profoundly Europa violates our expectations of habitability. Europa orbits Jupiter at a distance of about 670,900 kilometers, completing a full orbit every 3.55 Earth days. This orbit places Europa deep within Jupiter's powerful gravitational and magnetic influence. Jupiter is not just massive, it is violent, emitting intense radiation belts capable of killing unprotected humans in minutes. Europa's surface is constantly irradiated by high-energy electrons, ionized particles, extreme electromagnetic forces. From a surface perspective, Europa is lethal. And yet, beneath this radiation-blasted crust lies something paradoxical: movement, warmth, and water. Europa's exterior is composed almost entirely of water ice. Unlike rocky moons, Europa reflects sunlight with a pale, cracked brightness, giving it a smooth, ghostly appearance. The surface is one of the youngest in the solar system, estimated to be between 40 to 90 million years old, far younger than most planetary surfaces. Why is it so young? Because Europa's surface is not static. It breaks, shifts, melts, refreezes, and reforms. Long linear cracks stretch across the moon like scars, some spanning thousands of kilometers. These fractures are not random. They indicate a crust that is flexing under internal forces, not merely cracking from impacts. There are very few craters on Europa. In planetary science, craters are clocks. Fewer craters mean continuous resurfacing, and resurfacing means energy from below. For most of human history, the idea of life without sunlight was unthinkable. Photosynthesis shaped our understanding of biology. Plants feed animals. Sunlight feeds plants. End of story. Europa shattered that story. In the late 20th century, scientists studying Earth's deep oceans made a discovery that would permanently alter how we define habitability: hydrothermal vent ecosystems. These ecosystems thrive kilometers beneath the ocean's surface, in total darkness, powered by chemical energy from Earth's interior. Life there feeds on hydrogen sulfide, methane, chemical gradients, not sunlight. Europa may host the same fundamental conditions, but on a planetary scale. Europa does not rely on the sun for warmth. Instead, it is heated from within by tidal forces generated by Jupiter's immense gravity. As Europa orbits Jupiter, it is constantly stretched and compressed. This process, called tidal flexing, generates heat through friction, much like bending a paperclip repeatedly causes it to warm. This heating prevents the subsurface ocean from freezing, drives geological activity, allows water to remain liquid for billions of years. Unlike Mars, which lost its heat early, Europa's energy source is ongoing and stable. Europa matters because it forces us to reconsider where life can exist. It suggests that oceans do not need sunlight, Ice does not mean death. Moons can be more habitable than planets. If life exists on Europa, it would mean that biology can arise in places once considered completely sterile. And if life can arise on Europa, then similar ocean worlds, of which there may be billions in the galaxy, could also host life. Europa is not just a moon. It is a proof of concept. Europa is a paradox, frozen on the outside, warm and dynamic within, deadly at the surface, potentially alive below. It represents the moment when humanity realized that the universe may be far more biologically generous than we imagined. Europa's hidden ocean was not revealed through a single dramatic discovery. Instead, it emerged slowly, piece by piece, through decades of careful observation, indirect measurements, and scientific skepticism. No spacecraft has ever drilled through Europa's ice. No camera has photographed its ocean directly, and yet today the existence of that ocean is considered one of the strongest conclusions in planetary science. This confidence comes from multiple, independent lines of evidence that all point toward the same conclusion. Beneath Europa's frozen surface lies a vast, global body of liquid water. One of the earliest clues came from Europa's surface itself. When scientists first examined high-resolution images sent back by NASA's Voyager missions and later by the Galileo spacecraft, they were struck by how unusual Europa looked. Unlike the Moon, Mars, or Mercury, Europa's surface is remarkably smooth. Large impact craters are rare, and those that do exist appear shallow and degraded. In planetary geology, this is a critical clue. Impact craters accumulate over time, so a surface with few craters must be geologically young or constantly renewed. Europa's surface appears to be continually resurfaced, meaning that old features are erased and replaced by new ones. Ice, unlike rock, can flow, fracture, melt, and refreeze, suggesting that Europa's crust is not a rigid, dead shell, but something dynamic and active. Covering this icy surface is an intricate network of dark lines, ridges, and bands that stretch for thousands of kilometers. These features resemble cracks in sea ice on Earth, but on a planetary scale. Some ridges appear doubled, as if the surface split apart, filled with material from below, and then cracked again. Others show signs of sideways movement, indicating that sections of ice have slid past one another. These patterns are extremely difficult to explain if Europa is frozen solid all the way through. They make far more sense if the ice shell floats atop a liquid or semi-liquid layer that allows the crust to move independently. Perhaps the most compelling geological evidence comes from regions known as chaos terrain. In these areas, the surface looks as though it has been shattered into enormous blocks of ice, rotated, tilted, and refrozen in place within a rough, hummocky matrix. The scene resembles broken ice on a frozen ocean after a thaw, when chunks of ice drift, collide, and then freeze again. The leading explanation is that warm water or slushy ice from below rose close to the surface, weakening and partially melting the crust. The ice above collapsed, broke apart, and then refroze as the water cooled. Chaos terrain strongly suggests that Europa's ice shell is interacting directly with liquid water beneath it. Geology alone, however, was not enough to confirm an ocean. The decisive breakthrough came from measurements of Europa's magnetic environment. During its multiple flybys in the late 1990s, the Galileo spacecraft carried a magnetometer designed to study Jupiter's immense magnetic field. Scientists noticed something strange when Galileo passed near Europa. The magnetic field around the moon was not constant. Instead, it changed in a way that suggested Europa itself was generating a secondary magnetic field in response to Jupiter's. This phenomenon is known as electromagnetic induction. When a conductive material is exposed to a changing magnetic field, electrical currents are induced within it, producing a secondary magnetic field. For this to occur on Europa, there must be a global, electrically conductive layer beneath the surface. Ice is a poor conductor, but salty liquid water is an excellent one. The simplest and most convincing explanation was that Europa possesses a subsurface ocean rich in dissolved salts. Alternative explanations were considered and tested. Could the signal come from metallic core? Europa is too small, and its internal structure does not support a large, molten metal layer. Could the ice itself conduct electricity? Only if it were extremely warm and saline, conditions that again point toward liquid water. Over time, the ocean hypothesis became the only explanation that fit all observations simultaneously. Further support came from gravity measurements. By tracking subtle changes in Galileo's motion as it flew past Europa, scientists were able to infer variations in the moon's internal mass distribution. These measurements are consistent with a layered interior, a rocky core, an overlying liquid ocean, and a floating ice shell. The way Europa responds to Jupiter's gravitational pull also suggests that its outer layer is decoupled from the interior, something that would be impossible if the moon were completely solid. Then came one of the most exciting discoveries of all, evidence that Europa may be actively venting water into space. In 2013, observations from the Hubble Space Telescope detected faint plumes of water vapor rising hundreds of kilometers above Europa's surface near its south polar region. These detections were challenging and initially controversial, but subsequent observations strengthened the case that Europa occasionally releases water through cracks in its ice. If these plumes are connected to the subsurface ocean, they represent a direct link between the hidden sea and the vacuum of space. This possibility transformed Europa from a distant, inaccessible world into a potentially reachable one. Instead of drilling through tens of kilometers of ice, future spacecraft might simply fly through these plumes and sample material originating from the ocean itself. Salts, organic molecules, or even microscopic life, if present, could be carried upward and ejected into space. Estimates of the ocean's size only deepen its significance. Models suggest that Europa's ocean may be between 60 and 150 kilometers deep, lying beneath an ice shell that varies in thickness. The total volume of this ocean likely exceeds that of all Earth's oceans combined. This is not a hidden lake or a regional sea. It is a global ocean encasing the entire moon, in direct contact with a rocky seafloor below. Contact with rock is crucial. On Earth, the interaction between water and rock drives chemical reactions that release energy and nutrients. If Europa's ocean touches its rocky mantle, similar processes could occur there. Water-rock interactions could produce hydrogen, methane, and other compounds capable of fueling chemical ecosystems. Taken together, these lines of evidence form a remarkably consistent picture. Europa's young, fractured surface points to movement and renewal. Chaos terrain suggests melting and refreezing from below. Magnetic measurements demand a conductive, salty liquid layer. Gravity data support a layered interior. Water vapor plumes hint at active exchange between ocean and surface. Each piece alone might be questioned, but together they converge on the same conclusion. Europa is not merely an icy moon with a theoretical ocean. It is an active world with a hidden sea that has likely existed for billions of years. The question is no longer whether this ocean exists, but what it is like within that dark, pressurized environment, and whether it has the chemistry and energy necessary to support life. Europa's ocean should not exist. By all ordinary standards of planetary physics, a small moon orbiting so far from the sun should be frozen solid from surface to core. Sunlight at Jupiter's distance is weak, providing barely 4% of the energy Earth receives. If Europa depended on solar heat alone, its water would have frozen billions of years ago, locking the moon into permanent geological death. And yet the ocean persists. The reason lies not above Europa, but around it, within the immense gravitational grip of Jupiter. Europa is caught in a constant gravitational struggle. As it orbits Jupiter, it does not travel in a perfect circle. Instead, its orbit is slightly elliptical, stretched and maintained by a gravitational resonance with two neighboring moons, Io and Ganymede. This resonance prevents Europa's orbit from becoming circular and ensures that Jupiter's pull on Europa constantly changes. When Europa moves closer to Jupiter, it is squeezed by gravity. When it moves farther away, that squeezing relaxes. This rhythmic stretching and compression happens continuously, orbit after orbit, day after day, year after year. This process is known as tidal flexing, and it is the single most important energy source on Europa. The effect can be compared to bending a metal wire back and forth. Each bend generates heat through internal friction. On Europa, the scale is planetary. The Moon's interior flexes under Jupiter's gravity, generating heat deep within its rocky mantle and icy shell. This heat migrates upward, preventing the subsurface ocean from freezing and driving geological activity within the ice. The amount of energy involved is enormous. Although Europa is much smaller than Earth, the tidal forces acting upon it are far stronger than the gravitational interactions that drive Earth's ocean tides. Europa is locked into a gravitational dance so intense that it effectively turns Jupiter into a cosmic furnace, endlessly feeding energy into the Moon's interior. This heating is not evenly distributed. Models suggest that tidal energy is concentrated in certain regions of Europa's ice shell and upper mantle, creating zones of warmer, thinner ice. These regions may explain why Europa's surface is so fractured and why some areas show signs of recent resurfacing. Where heat builds up, ice softens, cracks, and may partially melt. Where heat diminishes, ice thickens and stiffens. Over time, this uneven heating creates stress patterns that tear the surface apart. Beneath the ice, tidal heating plays an even more critical role. It maintains the subsurface ocean in a liquid state despite surface temperatures cold enough to freeze carbon dioxide solid. The ocean is likely not uniformly warm, but rather thermally stratified. Warmer water may rise from deeper regions, while cooler water sinks, creating slow but persistent ocean currents. These currents are essential because they help distribute heat and chemicals throughout the ocean, preventing it from becoming stagnant. The heat source does not end at the ice-ocean boundary. Beneath the ocean lies Europa's rocky mantle, and this is where some of the most intriguing possibilities for life emerge. If tidal heating is strong enough, it may partially melt portions of this rocky interior, allowing volcanic or hydrothermal activity to occur on the ocean floor. On Earth, similar processes create hydrothermal vents, cracks in the seafloor where superheated, mineral-rich water gushes into the ocean. These vents are among the most biologically productive environments on our planet. Entire ecosystems thrive around them, independent of sunlight. Bacteria use chemical energy from the vent fluids to build organic matter, forming the base of complex food webs that include worms, crustaceans, and even fish. The discovery of these ecosystems transformed our understanding of life's limits. If Europa hosts hydrothermal vents, the implications are profound. Such vents would provide three crucial ingredients for life: heat, chemical energy, and a steady supply of nutrients. Water interacting with hot rock can produce hydrogen, methane, and other reduced compounds. These molecules can fuel metabolic reactions, allowing microorganisms to survive and reproduce in complete darkness. Evidence for this kind of activity on Europa is indirect but compelling. The ocean's contact with a rocky seafloor is supported by interior models and density measurements. The presence of salts in the ocean suggests prolonged water-rock interaction. Some surface materials appear to contain compounds that could originate from the interior, transported upward through cracks and fractures in the ice. While none of this proves active hydrothermal vents exist today, it strongly suggests that Europa has, or once had, the internal conditions necessary to support them. Another important aspect of Europa's energy system is its longevity. Many worlds in the solar system experienced brief periods of warmth early in their history, followed by long eras of freezing and inactivity. Mars, for example, once had liquid water on its surface, but lost much of its internal heat relatively quickly. Europa is different. As long as Jupiter exists and Europa remains locked in its orbital resonance, tidal heating will continue. This means Europa's ocean may have been stable for billions of years. Time matters enormously when it comes to life. Life does not appear instantly. It requires long periods of chemical experimentation, gradual increases in complexity, and sustained environmental stability. A short-lived ocean might never develop life, even if conditions were briefly favorable. A long-lived ocean, on the other hand, offers countless opportunities for chemistry to organize itself into something living. The combination of tidal heating and orbital stability makes Europa especially compelling. Its ocean is not a temporary accident, but a persistent feature of the Moon's existence. Even if conditions within the ocean fluctuate, the system as a whole remains active over geological timescales. This persistence dramatically increases the chances that life could arise and survive. However, tidal heating is a double-edged sword. Too little heating and the ocean freezes. Too much heating and the ice shell becomes unstable, potentially exposing the ocean to the harsh radiation environment at the surface. Europa appears to sit in a delicate balance between these extremes. Its ice shell is thick enough to shield the ocean from radiation, yet thin and dynamic enough to allow material exchange between the surface and the ocean below. This balance may be one of Europa's greatest strengths as a potential habitat. The ice acts as both a barrier and a bridge, protecting life while still allowing nutrients and chemicals from the surface to reach the ocean. Radiation at the surface can break down simple molecules, creating oxidants such as oxygen and hydrogen peroxide. If these oxidants are transported downward through cracks or melting ice, they could provide additional chemical energy to any life in the ocean, much like oxygen fuels complex life on Earth. In this way, Europa's energy system is not simple but interconnected. Gravitational forces generate heat. Heat drives geological activity. Geological activity enables chemical exchange. Chemical exchange creates energy gradients. Energy gradients are the foundation of metabolism. Europa is not warmed by a star. It is warmed by gravity itself. Understanding this engine beneath the ice changes how we think about habitable worlds. It suggests that life may exist far from stars, hidden beneath ice shells, powered by the relentless pull of massive planets. If Europa can sustain an ocean through tidal heating alone, then similar moons orbiting gas giants throughout the galaxy may be common, and many of them may harbor environments where life could exist. Water is the foundation of life as we know it, but water alone is not enough. A perfectly pure ocean, stripped of chemistry and energy gradients, would be biologically sterile no matter how vast it might be. To evaluate Europa's true potential for life, scientists must look beyond the presence of liquid water and examine what is dissolved within it, how those substances interact, and whether the ocean contains the raw materials necessary for biology to emerge and persist. This brings us to the chemical heart of Europa's hidden sea. From the earliest stages of Europa's formation, chemistry has played a central role in shaping its interior. Europa likely formed from a mixture of rock, metal, and ice in the early solar system. As internal heating melted its ice, liquid water came into prolonged contact with the moon's rocky mantle. This interaction is crucial because water flowing over rock triggers chemical reactions that release elements and compounds into solution. On Earth, this process enriches oceans with salts, metals, and nutrients. There's strong reason to believe the same is true for Europa. Multiple lines of evidence indicate that Europa's ocean is not fresh water, but salty. The magnetic field measurements that revealed the ocean's existence also suggest high electrical conductivity, which implies a significant concentration of dissolved ions. Surface observations support this conclusion. Spectral analysis of Europa's surface has detected materials consistent with salts such as magnesium sulfate, sodium chloride, and possibly sodium carbonate. These compounds are thought to originate from the ocean below and be transported upward through cracks, plumes, or slow cycling of the ice shell. Salts are more than a chemical detail. They influence how water behaves under pressure, how it circulates, and how it interacts with organic molecules. A salty ocean is more chemically active, capable of sustaining complex reactions over long periods. On Earth, saltwater environments are rich in microbial life, especially in extreme conditions where organisms exploit chemical gradients rather than sunlight. Carbon is another essential ingredient for life, and Europa appears to have access to it. Carbon-bearing compounds have been detected on the surface, likely delivered by comets, asteroids, and interplanetary dust over billions of years. Jupiter's intense radiation environment plays a surprising role here. That when high-energy particles strike Europa's icy surface, they break apart water molecules and carbon compounds, creating a variety of reactive chemicals. These include simple organics, carbon dioxide, and oxidants. Radiation, often seen as purely destructive, may actually contribute to Europa's habitability. By breaking down surface molecules, radiation creates chemical energy stored in oxidized compounds. If these compounds are transported downward into the ocean through fractures or melting ice, they can react with reduced materials from the seafloor. This interaction between oxidants from the surface and reductants from the interior creates chemical gradients. And chemical gradients are one of the most powerful drivers of metabolism. On Earth, life exploits gradients wherever they exist. Oxygen-rich water meeting oxygen-poor environments fuels respiration. Sulfur compounds feeding bacteria at hydrothermal vents power entire ecosystems. Europa may host similar interfaces where chemicals from different sources meet and react. Even without sunlight, such gradients can sustain life. The seafloor itself is likely a major chemical engine. If Europa's ocean rests directly on a rocky mantle, water-rock interactions could produce hydrogen through a process known as serpentinization. This reaction occurs when water reacts with certain minerals and rock, releasing hydrogen gas and heat. On Earth, hydrogen is a key energy source for many microorganisms living deep underground and around hydrothermal vents. These organisms use hydrogen to convert carbon dioxide into organic matter, forming the base of self-sustaining ecosystems. Methane is another molecule of interest. Methane can be produced through both biological and non-biological processes, and it serves as a powerful energy source for microbes. If methane exists in Europa's ocean, it could support metabolisms similar to those found in Earth's deep biosphere. While methane has not yet been definitively detected on Europa, the chemical conditions necessary for its formation may be present. Nitrogen, phosphorus, sulfur, and trace metals are also critical for life. These elements form the backbone of proteins, DNA, cell membranes, and enzymes. Europa's rocky interior likely contains many of these elements, which could be leached into the ocean over time. The long-term stability of the ocean increases the likelihood that such elements have accumulated to biologically useful levels. One of the most important questions concerns pH. Life on Earth can tolerate a wide range of acidity, but extreme conditions can limit biological diversity. Models of Europa's ocean chemistry suggest it may be slightly alkaline, similar to Earth's oceans or some hydrothermal systems. An alkaline environment would favor certain types of chemical reactions, including those thought to be important for the origin of life. Temperature also affects chemistry. Europa's ocean is likely cold by Earth standards, perhaps only a few degrees above freezing in many regions. However, near the seafloor or in zones of active heating, temperatures could be significantly higher. This thermal diversity would allow different chemical pathways to operate simultaneously, increasing the complexity of the environment and expanding the range of possible habitats. Importantly, Europa's chemistry is not static. The Moon's ice shell acts as a slow conveyor belt, cycling material between the surface and the ocean. Surface ice exposed to radiation becomes chemically altered, enriched with oxidants and new compounds. Over time, some of this ice may sink or melt, carrying its chemical cargo downward. At the same time, Ocean material may be transported upward through fractures, plumes, or convection. This exchange ensures that Europa's ocean is continually refreshed with new chemical ingredients. Taken together, these factors paint a picture of an ocean that is chemically alive, even if it is biologically unknown. Salts enhance conductivity and circulation. Carbon provides the backbone for organic molecules. Radiation creates reactive compounds at the surface. Water-rock interactions generate energy-rich chemicals at the seafloor. Long-term stability allows these processes to persist and interact over billions of years. Europa's ocean is not just water trapped beneath ice. It is a dynamic chemical system shaped by gravity, radiation, and geology. Such systems are precisely where life thrives on Earth, often in places once thought impossible. While no direct evidence of life has yet been found, the chemistry of Europa's ocean satisfies many of the fundamental requirements for biology. To imagine life on Europa, scientists first had to break free from surface-based thinking. For most of human history, life was associated with sunlight, warmth, and open air. Oceans were thought to be lifeless in their deepest regions, too cold, too dark, and too starved of energy to support biology. That assumption collapsed in the late 20th century, when exploration of Earth's deep oceans revealed ecosystems so alien that they reshaped biology itself. These environments now serve as the most powerful analogs for what may exist beneath Europa's ice. In 1977, a deep-sea expedition exploring the Galapagos Rift discovered hydrothermal vents along the ocean floor. These vents released superheated water rich in dissolved minerals and chemicals. Instead of barren emptiness, scientists found dense communities of living organisms clustered around these vents. Giant tube worms, clams, shrimp, and microbial mats flourished in total darkness, thousands of meters below the surface. No sunlight reached these depths. Photosynthesis was impossible. Yet life thrived. The foundation of these ecosystems was chemosynthesis. Rather than using sunlight to convert carbon dioxide into organic matter, microbes used chemical energy stored in compounds such as hydrogen sulfide, methane, and hydrogen. These microbes formed the base of a food web that supported increasingly complex organisms. This discovery demonstrated a profound truth. Life does not require sunlight. It requires energy, chemistry, and stability. Europa's ocean may offer similar conditions. Like Earth's deep oceans, it is permanently dark. Light cannot penetrate tens of kilometers of ice. If life exists there, it must rely on chemical energy rather than solar energy. The likely sources of that energy mirror those found on Earth's seafloor. Water-rock interactions, tidal heating, and possible hydrothermal activity could supply a steady flow of reduced chemicals. At the same time, oxidants created on Europa's surface by radiation could be delivered downward, creating powerful chemical gradients. On Earth, some of the most ancient lineages of life are found in extreme environments that resemble what Europa's ocean might be like. In the deep subsurface biosphere, microbes live kilometers below the surface, isolated from sunlight for millions of years. They survive by feeding on hydrogen produced by radioactive decay and water rock reactions. These organisms grow slowly, sometimes dividing only once in hundreds or thousands of years, yet they persist. Their existence proves that life can survive with minimal energy input, as long as conditions remain stable. Another analog comes from subglacial lakes in Antarctica, such as Lake Vostok. This lake has been sealed beneath kilometers of ice for hundreds of thousands, possibly millions of years. Despite this isolation, evidence suggests that microbial life may exist within it. The lake is cold, dark, and nutrient-limited, yet it appears capable of sustaining life. Europa's ocean shares many of these characteristics, though on a vastly larger scale. Even in Earth's coldest oceans, life finds a way. In polar seas beneath thick ice cover, ecosystems function with extremely low temperatures and limited nutrient input. Microorganisms adapt by slowing their metabolism, altering their cell membranes, and developing enzymes that function efficiently in the cold. If life arose on Europa, it would likely exhibit similar adaptations, optimized for survival in an environment where energy is scarce and conditions change slowly. Europa's gravity is lower than Earth's, and its ocean exists under immense pressure from the overlying ice. Life there would experience conditions unlike anything on the surface of our planet. Pressure alone does not prevent life. Earth's deepest ocean trenches experience pressures hundreds of times greater than at the surface, yet organisms survive there. On Europa, pressures could be even higher, especially near the seafloor. Any life forms would need to be structurally adapted to withstand these forces, perhaps with flexible membranes and slow, resilient metabolisms. If life exists on Europa, it is most likely microbial. Simple, single-celled organisms are extraordinarily adaptable and dominate Earth's biosphere in both number and diversity. They can survive extremes of temperature, pressure, acidity, and radiation. Complex multicellular life requires far more energy and environmental stability. While it is not impossible that Europa could host simple multicellular organisms, most scientists consider microbial life the most realistic possibility. Such organisms might resemble Earth's archaea or bacteria, using chemical reactions to extract energy from their environment. They could live suspended in the ocean, clustered around chemical sources on the seafloor. To avoid false conclusions when searching for life, Europa's surface is one of the most radioactive environments in the solar system. Jupiter's immense magnetic field traps charged particles that bombard Europa relentlessly. Radiation levels on the surface are high enough to destroy organic molecules in a matter of days or weeks. Any life exposed directly on the surface would be quickly sterilized. This makes the ice shell not just a barrier, but a necessity. Beneath several kilometers of ice, radiation fades to harmless levels, creating a protected environment where biology could persist. Pressure is another challenge. Europa's ocean lies beneath tens of kilometers of ice, meaning the pressure at the seafloor could be hundreds of times greater than Earth's atmospheric pressure. Yet pressure alone does not forbid life. On Earth, organisms thrive in the deepest ocean trenches under crushing conditions. Life adapts not by resisting pressure, but by harmonizing with it at the molecular level. Isolation presents a subtler obstacle. Europa's ocean is sealed off from the surface world, potentially for millions of years at a time. Nutrient flow may be slow. Energy may be scarce. Life in such an environment would likely evolve toward extreme efficiency. Growth would be slow. Reproduction would be rare. Survival, not expansion, would define existence. For scientists, Europa's ice shell is the greatest technical challenge. Drilling through tens of kilometers of ice is far beyond current capabilities. This is why upcoming missions focus on indirect exploration. NASA's Europa Clipper mission will conduct dozens of close flybys, mapping the ice shell, measuring the ocean's depth, analyzing surface chemistry, and sampling any water plumes that erupt into space. The European Space Agency's JUICE mission will complement this effort by studying Jupiter's moons as a system. Future missions may include landers capable of analyzing surface ice for biosignatures, and eventually cryobots, robotic probes designed to melt through ice and release autonomous submarines into the ocean below. These missions raise ethical concerns as well. If Europa hosts life, humanity must ensure that exploration does not contaminate or harm an alien ecosystem that has existed untouched for billions of years. The discovery of life on Europa would be one of the most profound moments in human history. It would prove that life is not a rare accident confined to Earth, but a natural outcome of chemistry and physics under the right conditions. Even the discovery of simple microbial life would redefine biology, philosophy, and our understanding of our place in the universe. And if Europa is lifeless, that answer would matter too. It would tell us that even when water, energy, and chemistry are present, life is not guaranteed. Either outcome reshapes how we search for life beyond Earth. Europa teaches us humility. It reminds us that life may exist in forms and places we never imagined, silent, unseen, thriving beneath ice in eternal darkness. The universe does not announce its secrets. It waits for us to learn how to listen.